Hello there, this is an Algebra 1 video, and we are getting started with Chapter 6. This is Section 1, Graphing Systems of Equations. And before we get started with any of the examples and stuff, I kind of need to remind you a little bit about solutions and equations and how that all works, because right now we're going to be solving a system of equations, and you're not a system of equations unless you have more than one equation in the problem. So what I have here on the board is basically two equations, y equals 2x plus 3 and y equals negative x minus 6. Typically we use a little curly bracket like that to indicate that we have a system because there's two equations combined. And so before I get going, I need to explain to you, hopefully you still remember how to graph. So if I wanted to graph y equals 2x plus 3, which is the blue line that you see in my graph here, the y-intercept is 0, 3. So you can see x is 0, y is 1, 2, 3. There's my point there. And then my slope is 2 over 1. So from this y-intercept, I go up 2 units over 1. Or you can go backwards and go down 2 units and then left 1. And then I get the blue line. And then for y equals negative x minus 6, I plot the y-intercept, which is negative 6, so there's my negative 6. And then my slope is negative 1, so I can go down 1, right 1. Or if I want to go backwards, I can go up 1, left 1, and still be on the line. So what I wanted to talk to you guys about, what you see on the board, is aside from the fact that there's a blue line and a red line, you see these other dots on the graph that are basically in green. I've got the point here. This point is positive 2, negative 2. Sorry about that. This point is positive 2, negative 2. This point here is negative 1, positive 1. And then this point here is negative 2, negative 4. And so what I wanted to show you with that is how solutions work. You are not a solution of the equation unless you are on the line that represents that equation. So for example, y equals 2x plus 3 is the equation of the blue line. And this point, negative 1, 1, is on the blue line. So I would expect that this point, when I plug in the x and y values to y equals 2x plus 3, I should get a true statement. And I'm going to do that now. So if the y coordinate is 1, and the x coordinate is negative 1, and then plus this is y equals 2x plus 3, the blue line, then I'm going to get 1 equals negative 2 plus 3, and 3 minus 2 is 1, and 1 does in fact equal 1, so it works. It's a solution. Also, I'm going to check negative 2, negative 4, but negative 2, negative 4, this point here is on the red line, so I would expect that negative 2, negative 4 be a true statement on the red line, which is the equation y equals negative x minus 6. So if I check that one, the y coordinate here is negative 4, and then negative x, and x is negative 2, minus 6. So here I have y equals negative x minus 6. Now be careful here because it is negative x, and x is already negative. So these two negatives make a positive, and 2 minus 6 is in fact negative 4, and it checks because it's supposed to equal negative 4. So when you're on the equation of the line, when you're on the actual line itself, it's because you're a solution to that equation. The point 2, negative 2 is neither on either, it's not on either line. So when I plug in 2, negative 2 to either equation, it shouldn't make sense. It should not be a true statement. And I'm going to check that now. So this y coordinate is negative 2 equals 2 times 2 plus 3. So I'm plugging it into the y equals 2x plus 3. So negative 2 equals, 2 is 4 plus 3. And 4 plus 3 is 7. So negative 2 is supposed to equal 7, but it doesn't. And that's supposed to happen because it's not a solution. If I plug that same point into negative x minus 6, I'm still going to get the same thing. I'm going to get y is negative 2, and then negative x, and in this case x is positive 2, minus 6. So now I'm plugging it into y equals negative x minus 6. So I get negative 2 minus 6, which is negative 8. And my statement reads negative 2 is equal to negative 8, which it's not. So you see, the idea of being on the graph means that you're a solution to the equation. Being off the graph means you're not a solution. So that's all important when you talk about graphing systems of equations, because when you graph a system, our goal now is to find a point. There's several points on the blue line that will make this equation true. There are several points on the red line that will make the second equation true. But our solution for a system is where the two lines cross. So I want a point that is on both lines at the same time. So this point is a solution to y equals 2x plus 3. And this point is a solution to y equals negative x minus 6. But this point here, the black dot, is the only solution to both lines because it happens to be on the blue line and the red line at the same time. And when I check that, I can put y is negative 3, 2 times negative 3 plus 3, because in this case both x and y are negative 3. So negative 3 equals negative 6 plus 3, and lo and behold, negative 3 does in fact equal negative 3. It checks. I check the second equation and I get y is negative 3, x is negative 3. So these two negatives make a positive, and 3 minus 6 is negative 3. And again, it checks. So this is the solution to my system. All right, so it's important that we understand the difference between being a solution to one equation. There are several solutions to the blue equation, several solutions to the red equation, but there's only one solution for the system, the place where the two lines cross, basically. So that's kind of what we're going to be doing today. And so that leads us to these possible solutions. We have three possible scenarios when you're graphing systems of equations. The first scenario is what you just saw in the previous example, where you have two distinct lines that intersect one time, and so they will have one solution, the point where the two lines cross. This system is called consistent and independent. It has one unique solution, unique meaning that that's only one solution, there's exactly one. And when you're looking at the equations themselves, the two equations will have different slopes, just like they did in this case. This one had a slope of 2, a slope of negative 1. They have different slopes. That's just going to help you later on in your homework. Then we have a second scenario, and what I tried to show you here is basically sometimes when you graph the two lines, they actually end up being the same exact line. And that's kind of what I'm trying to do here. Technically, they're not on top of each other because I wanted you to see both the blue and the red. But the idea here is that you have the exact same line. There's two equations, but they actually form the exact same line. In that case, you have what we call a consistent and dependent system. And then as far as when will they cross, you won't have a unique solution like in that case. These two lines, when you think about when they cross, when they're touching, if the two lines are on top of each other, they're always touching. And therefore, you have infinitely many solutions. And the equations of the lines in this case will look like same slope, same y-intercept. And that's important because that's different from our third scenario, which also has the same slope. So both of these scenarios have same slope. But in this case, you have the same slope and same y-intercept because they're the exact same line. But in this case, they're not the same line, but they are parallel lines. These are parallel lines. And so we said earlier that the solution to the system is the point where the lines cross. Well, parallel lines never cross. So in that case, you would have no solution. The system is called inconsistent, so we have these two parallel lines here. And the equations would look like same slope, but different y-intercepts, unlike this one where the same slope and the same y-intercept. So those are the possible solutions that you can have. And so now I want to do some examples with you so we can kind of apply what we're talking about here. So it says, use the graph at the right to determine whether each system is consistent or inconsistent, and if it is independent or dependent. Okay? So we've got 4 lines, and they're all different colors. So we've got this red line is negative 2x minus 5. The green line is negative 2x plus 3. The pink line is x minus 5, and the blue line is y equals 2x plus 3. So we're only dealing with 2 lines at a time in each scenario. So you're going to do these two down here, and I'm going to do these up here. So when I look at the part A, it's negative 2x plus 3, which is the green line, and then x minus 5, which is the pink line. So they're asking me what kind of a system the green line and the pink line make. And since the green line and the pink line cross one time, they're not going to be parallel. So it's not going to be an inconsistent system. It's going to be a consistent and independent. Okay? So it said to determine each system. Okay, that's it. So that's what we want to say for that one. Now in this case, they want me to check negative 2x minus 5, which is the red line, and negative 2x plus 3, which is the green line. So now we're looking at the red and the green, and those lines appear to be parallel, and we can double check that because they both have the same slope, but they have different y-intercepts. So that means that these are going to be parallel lines, and they're going to be inconsistent. Had they been the same line, then you would put consistent and dependent. But in this case, it's inconsistent. All right, and that's again based off of this information. All right, we can also see from the consistent and independent that you're supposed to have different slopes. And when we look at these two, they do have different slopes, so it all works out. So now I want you to try to do yourself number 1, and then we will go on to our next example. So I will say right now that when you are graphing equations in this section, it's very important that your graphs are very, very accurate. I highly encourage you, recommend you to use graph paper and to not try to make your graphs really small, to use a ruler, because the slightest crooked line can mean that the two lines will cross in the wrong spot, and then you will have the wrong answer. And so that's just going to be unfortunate if you're doing if you're understanding and conceptually you're understanding how to do it. If you're just being lazy and you're not drawing straight lines, they're not going to cross in the right spot, and then you're going to have problems the whole time. So I'm going to test to graph each system, and after I've graphed it, determine the number of solutions that it has, and if it does have one solution, then they want us to name that solution. So I'm going to graph negative 3x plus 10, so my y-intercept is going to be at 10 right here. Now I'm going by 2's on the y-axis, but by 1's on the x-axis. So it says negative 3x, so my slope is negative 3, but I don't want to go down 3 because I'm going by 2's. So I need to figure out a way that I can go down by 2's and it still equal negative 3. Well, it's true that negative 6 divided by 2 is the same thing as negative 3. So instead of going down 3 over 1, I'm going to go down 6. So down 2, down 4, down 6. And then I'm going to go to the right 2 units. And remember that on the x-axis I'm going by 1's. So I'm going to go to 2 units right about there. And then I'm going to go down 2, down 4, down 6, over 2. I just have to do that a couple of times so that I can guarantee that my line be as straight as possible. Okay, so there goes my first line. And then I have x minus 2, and again I'm going by 2, so my intercept is right here at negative 2. And now my slope is 1 to 1. But again, I don't want to go up 1 because it's going to be right in the middle. I want to go up by 2. So if my slope is 1, that's the equivalent of 2 over 2. So I can go up 2 over 2, up 2 over 2. Graph that line. Okay, and now I can see that this is going to be a consistent and independent system, so I'm going to have one solution. And since I only have one solution, they're asking me to actually name that solution. So I can see that that's going to, x is 1, 2, 3. So x is 3, and y appears to be 1. It's halfway between here and here, and this is going by 2's, remember? So it's 3, 1. And you can even check that by plugging it in. If I plug in a 3 for x, then that's 3 minus 2, which is 1, so y would equal 1, and it works. If I plug in the 3 to the top equation, I get negative 3 times 3, which is negative 9, and 10 minus 9 is 1, which would be the y-coordinate. So this is the right solution. But again, it's just important that you draw your graphs very carefully. All right. So over here, I have some equations that I'm going to draw And now these equations are not in y equals mx plus b, but have no fear that A, you could transform it into y equals mx plus b, or you could use standard form, which is the hide and divide method of graphing. So I'm going to do hide and divide, so I'm going to hide the x. And when I hide the x, I get negative 1 divided by negative 1, which is positive 1. And then when I hide y, I get negative 1 divided by 2, which is negative 1/2. In the second case, I hide the x, and I get 6 divided by negative 2, which is negative 3. And then when I hide the y, I get 6 divided by 4, which is 3/2. Okay? So now I just use my x and y intercepts to graph these lines. So the first one, I'm going to get 0, 1. So x is 0, y is 1. And then negative 1/2, 0. So negative 1/2 will be right about here. And then I connect those two little guys. And my second line is going to be 0, negative 3. So 1, 2, negative 3. And 3/2, 0. So 1.5. So there's 1. 1.5 is right about here. And it looks like these two lines are going to be parallel. And when they're parallel, you have no solution because the system is inconsistent. So there are no solutions, and since there's no solution, we don't have to name our solution. And that's how you do that, little guy. And so I want you to try this one on your own. Remember that if they're in standard form, like this one and these over here, that you're welcome to use hide and divide to graph it, or you can transform it into y equals mx plus b and then graph it. All right, and I believe this is our last example here. It says, the number of girls participating in high school soccer and track and field has steadily increased over the past few years. Use the information in the table to predict the approximate year when the number of girls participating in these two sports will be the same. Okay, so basically what we're going to do is we're going to take this information from our table and make it into an equation. Basically, it's telling us that for soccer, you had 345 girls, but an average rate of increase of 8 per year. So basically that means that this equation is going to end up being y equals 8x plus 345. So you start off with 345, and then every year you're adding 8, and x is the years. The second equation would then be y equals 3x plus 458, because in the case of track and field, which is what the TNF stands for, you're starting with 458 girls, and then you're adding 3 every year. So in the first case, you're starting off with fewer, but you're adding more per year. Here you're starting off with more, but you're adding fewer per year. And the question is, when will the number of girls participating in these two sports be the same? So what we want to do is basically graph them and then see where they cross, because that's when they would be the same. I'm not sure why that turned off. But 345, 8x equals 345. So my y-intercept is 345, so here's 320, and we're going by 40s here. This is 240, 280, 320, and this would be 360. So somewhere in between here, you're going to have your y-intercept of 345, and then you're going to go up 8 and over 1. But the problem with that is, again, you don't really know, like, go 8 over 1, right? So I want to convert 8 to a bigger number. So 40 divided by 5 is the same thing as 8. So for me, since each of these tick marks is 40, it's a lot easier for me to go up 40 and then over 5. So on the bottom, I'm going by 2s. 2, 4, 6, 8, 10, 12, okay? So 2, 4, here's 5. So I'm guessing it's going to be right about there. It's not perfect, but it should probably be a little bit lower. So hold on here. 1, 2, 4, 5 is going to be right there. And then we're going to go up 40, so we're going to go right. Oh, sorry. I just really want to get this accurate so I can get as close to my answer as I need to be. There we go. All right, so I get that line. For the 458, I'm going to go, here's 440, and then this is 480, so 460 would be somewhere like in the middle, a little bit underneath. And then my slope here is up 3, but again, I'm going by 40s. So, let's see. I'm going to go up by 36. I'm going to say the slope of 3. If I go up by 36 and divide it by 12, that's going to be 3. And the reason why I chose 36 is because it's close to 40. So from here to right about here would be me going up 40. But I don't want to go up a full 4, so it'll be a little bit lower than that. But I want to be all the way to 12. 2, 4, 6, 8, 10, 12. So that's going to be there. And then this guy is going to be there. Okay. So roughly, now obviously if I had paper, this would be a lot easier because I could use my graph paper, but it's kind of hard in this case. So basically I see that it's crossing right about here. My job is to kind of guess more or less what year that is. It says in what the approximate year when the number of girls participating in these two will be the same. So I'm trying to pick this guy right here. It looks like it's, there's my point. It looks like it's right around 20, a little bit before that. So let me double check that. So 20 years. So if it's 20 years, that's the approximate. The book might have a different answer, but that's okay. We're just trying to find the approximate. It looks like it's 20. And since we started in 2008, 20 years later would be the year 2028. It's an approximate year. It's not going to be exact. All right, so then you can try this little guy on your own. And once you have completed this example, you will have completed your notes for this lesson. And I will see you in class, and thanks for watching.